So hello everyone, today I'll be presenting a comparative reliability study of two major file system designs, journaling file systems and log structure file systems. My name is Asim and this presentation is based on my research paper following the IEE format. At the beginning, these two file system families solve the same problem, which is handling crashes safely, but they do it in a completely different ways. Today I'm going to explain why that matters, how they work internally, and what the real trade-offs are. So before we compare anything, let's talk about why reliability matters. So file systems operate in an unpredictable world. A sudden power loss or even a kernel panic or even though a loose SSD cable, all of these can interrupt writes at the worst possible time. And when that happens, the file system may be left in a half old or even half new state. So some metadata might be updated, some not. Blocks may be allocated but not referenced. Directories may point to files that no longer even exist. So these inconsistencies can cause real-world problem, such as lost user data. The user maybe lose the data, or even application crashes, or even the longer recovery time for the full FSCK scans, or even volumes marked dirty. So our goal is very clear, which is even when a crash happens at the worst moment, the file system must stay consistent. So talking about, let me show you the inconsistencies happen. So let's see how the inconsistency happens. So inconsistency happens normally when a write operation updates three things. When it updates the data blocks, the inode metadata, or even the allocation bitmap. All of these updates happens in place on the disk. So imagine a crash happens between step 2 and step 3. Some new blocks are allocated, but the metadata does not point to them. Now you have to deal with three things, which is dangling references, orphan blocks, or even incorrect inode links. This is how simple write operation becomes a deep consistency problem. So two reliability approaches to solve this, the file system designers took two different approaches. One is journaling, which is journaling file systems. And journaling file systems maintain a redo log, also called a journal, before modifying the disk. They first record the operation in the journal, and this gives strong consistency, but adds also an overhead. And secondly, we have log structure file systems. Instead of updating in place, they treat the disk like one big append-only log. All writes, data, metadata, inodes are appended at the end, as you can see in the figure. So nothing is overwritten, everything is versioned. Both approaches are crash safe, but the internal mechanism and recovery behaviors are completely different from each other. So journaling file systems and log structure file system, both of them are not the same. So let's break it down for how journaling works. When an application wants to write something, the file system does not update the real disk immediately. Instead, it performs the update as a transaction. The metadata changes are copied into the journal, as we talked in the journaling. And only when everything is safely written to the journal, then we write the real metadata to disk. And finally, we checkpoint and free journal space. This gives us atomicity, either the entire transaction is applied or none of it is. And what happens actually when the journaling gets crashed and the recovery of the crash? What happens during a real crash is when the system reboots, the recovery thread scans the journal from the last checkpoint. So if it finds complete transaction, meaning it has a commit record, it replies it safely. So it replies it safely because it has a commit record. And if a transaction is incomplete, it gets discarded. So journaling gives us predictable recovery time, usually under 1 second, because the journal size is small and bounded. This is why journaling file systems avoid long FS. So now let's switch to log structure file systems. So log structure file systems has a completely different philosophy, which is never overwrite anything and also append everything at the end of the log. So instead of modifying blocks in place, block structure file system writes it as data blocks, inodes, directory blocks, indirect blocks, and also a segment summary. So all into a sequential segment in memory. And then it flushes that entire segment to the disk. This gives extremely high write throughput, especially for many small files. Internally, log structure file systems groups updates into segments. Each segment contains data, metadata, inodes, and summary of what's inside the segment, because everything is sequential. Writing becomes as fast as streaming to an SSD. But this design also means that old blocks become obsolete. They are still on disk but no longer referenced. We need cleaning to reclaim space. So for cleaning, and cleaning is actually the heart of the large file, for the locked structured file systems. So for cleaning, when a segment fill up, the cleaner process scans them to identify. So the segment is already full up. The cleaner process scans this and scans everything in it. So to identify the live blocks, which is still in use, and dead blocks, which is overwritten. Then it rewrites the live blocks into a new segment and frees the old one. So cleaning is powerful but also expensive. And if the cleaner becomes starved, the file system might think space is free while actually containing data. So, so this one causing silent space loss. And log structure file system recovery is very different from journaling. At mount time, logged structured file system reads the most recent checkpoint and then it scans all segments written after that checkpoint, and this is the rule forward step. And using segment summaries, it reconstructs the latest consistent state. So recovery time depends on how much dirty data exists since the last checkpoint, and this can be 1 second or even 8 seconds depending on how much was written. And this graphs, as you can see here, shows the difference clearly. Journaling has very stable recovery time, usually under 1 second, as you can see, because the journal is small, but the logged structured file system recovery grows with workload from 1 to 8 seconds, which is too much because it must roll forward entire segments. This scalability trade-off depending on workload robustness. So conversion, uh, write amplification is also different because journaling, full journaling is around x2, while order mode is around 1.1x. So also for the log structure file system, it's at 80% full for around 1.2 and at 95% full or full up to 1.6. So log structure file systems performs better than journaling when there is lots of free space. But as disk fills the log structured file system amplification, cleaning becomes more expensive. Both file systems maintain strong metadata consistency, but through different mechanisms. Journaling ensures metadata is never partially updated. Log structure file system ensure consistency through segment, summarize, and checkpoint. However, log structure file system can suffer from lost segments if the cleaner fails to finish rewriting the live blocks. Journaling does not have this issue because every committed metadata update is in the journal. So this was all. Thank you for listening.